Welcome back. We continue our discussion on soft lithography, which we started in the previous class, and we already realized that soft lithography is a generic technique for patterning different types of polymers or soft materials, and is not limited like photolithography, which can pattern only a photoresist layer. We also realized one more thing, that unlike photolithography, which refers to a very specific technique, soft lithography talks about a suite of methods that are compatible for patterning polymers and soft surfaces. So, therefore, it is also important to classify and understand the different key techniques that constitute soft lithography. Classification itself can be a bit philosophical. So, how would you like to classify? Based on what would you like to classify these so called soft lithography techniques? One of the ways to classify is based on the nature of patterns you would like to create. What is the nature of patterns? You have seen some regular structure, and we are talking about nano and mesoscale structures, that is obvious, but even from photolithography you can in fact take the clue. Patterns can be primarily of two types, and those are either a topographic pattern or a chemical pattern. In fact, if you recall your discussion, our discussion on photolithography, photolithography at different stages makes both, though finally it makes a chemical pattern, because the final product after the doping reaction and etc., is a flat wafer which has domains of p and n type areas. So, this is in a way a chemical pattern. You should be able to appreciate it now. It is flat, so there is no topography, but in a run up to make this, as you now understand the method of photolithography, you should be able to recall that at two stages photolithography makes topographic patterns. One is a patterned photoresist layer, and then after you have performed the etching, one is the patterned barrier layer or the oxide layer. So, that is a topographic pattern. So, where you have structures like this. So, soft lithography is capable of making both. So, one of the classification, the other thing I must highlight, in the context of soft lithography, a chemical pattern typically refers to structures on a flat surface with different wettability areas. So, you essentially talk about a flat surface, which can be a wafer, which can be a metal coated glass, metal coated wafer, whatever. So, if you look at the line profile with an atomic force microscope or a surface profilometer, it will be flat, but these shaded areas refers to let us say surface energies gamma 1, and these areas let us say refer to gamma 2, and it is very common to have, let us say, gamma 1 is hydrophobic and gamma 2 is hydrophilic. So, you in the context of photolithography, in the context of soft lithography, you may refer to a chemical pattern as a surface which has spatially varying domains of different wettability areas, particularly let us say alternating patches of hydrophobic and hydrophilic domain. Much later when we talk about dewetting, you will see that these type of chemically patterned surfaces with alternating patches of hydrophobic and hydrophilic domain are excellent candidates for ordering the instability structures. So, this is one way of classifying methods that are capable of producing topographic patterns versus metals which are capable of producing let us say chemical patterns. The other another classification approach can be whether, and this is a pretty important one, whether you are using what is the nature of the stamp, whether it is a flexible stamp or it is a rigid stamp. And I already mentioned that there are certain questions often asked whether nano imprint lithography belongs to a soft lithography technique, or you would like to categorize it as an embossing technique and say that, well, it is not exactly soft lithography. And the reason the question is asked is nano imprint lithography in fact uses a rigid stamp. It is a rigid stamp, we will see what it uses. Unlike most other soft lithography techniques, which in fact uses a flexible stamp, and immediate question to us, so flexible stamp will be something like this. Immediate question to ask is what is the material of the flexible stamp, and it turns out that we have already discussed it. Yes, this is the most favored material for stamp making. In fact, the simplest technique, we will soon talk about it, replica molding. It is very simple, though the original paper was, I think, published in the Journal of Nature or Science. I think it was published in Nature about 20 years back. It actually makes this stamp for other techniques. So, as I said that this is again a philosophical difference or a pedagogic difference as to what type of stamp material you are using. Nano imprint lithography, let me just spend a minute, and when we discuss it in detail you will again see. The reason I consider, and many others consider, NIL to be also a soft lithography technique is, though it uses a rigid stamp, ultimately it is patterning a soft material. So, it is soft from that standpoint. The stamp might be hard, but ultimately it is performing its function on a soft material, and therefore, this is sort of a classification that I would prefer to use, and this is what I will be following for the whole of this course. So, I include NIL into this group, but I mention that it is actually an imprinting technique rather than a classical soft lithography technique, which requires a flexible stamp. So, the moment you are imprinting, you are bringing in a rigid stamp, and then you are actually applying pressure from outside, excess pressure from outside. But nonetheless, you are creating topographic structures with soft materials like polymers. So, therefore, I would consider it here, though the exact pattern transfer replication mechanism in fact is viscoplastic deformation of the polymer, because you are applying a lot of pressure. So, one of the advantages of soft lithography, what we mentioned, that it is a very gentle processing condition, is in fact not valid for nano imprint lithography. However, saying that, it is also a fact that nano imprint lithography is a technique which on its own merit has gone to the commercial level, and instruments are available for performing and implementing nano imprint lithography. It is a very simple technique and a very robust and useful technique. So, anyway, the way we will be looking at it is the imprinting based techniques and the classical soft lithography, which uses the flexible stamp, and then again we classify them into two broad categories, whether they are capable of creating a topographic pattern or a chemical pattern. And there is only one major technique that talks about fabrication of chemical patterns. We will learn that is micro contact printing. On the other side, for topographic patterns, there are various methods. As I mentioned, each one of these methods, it is not that you can also create chemical patterns by this method, that method, and things like that, but each of the method has certain uniquenesses, and that is why I have identified only these 5 methods, including nano imprint lithography, because if you understand their basic operational philosophy, you sort of understand most of the methods. Of course, if you are a practicing researcher in this area, you will come across very many different names, but you can immediately identify two things: how to which method it is closest to, and how exactly it is different from the parent method. So, we will be talking about these methods: nano imprint lithography, capillary force lithography, micro molding in capillaries, replica molding. This is the first one we will get started, because this sort of supplies the stamp for most other soft lithography technique. It is so simple that if you have Sylgard 184 at your disposal, you will be trying to do replica molding, and you actually do not need a lithographically fabricated stamp or anything. You can do it on a coin, and you can create a very beautiful replica of whatever I mean whatever is there on the surface of a coin or any hard material on a flexible matrix. It's pretty similar to sort of the way one makes a rubber stamp with some advancements, and these few methods we will discuss. So let's move on, and we have already talked about these classifications, but this resource will be with you. So material for replica molding is something we have already discussed. It's Sylgard 184. And in fact, those of you who have interest in microfluidics, another very advanced area where a lot of research in fact worldwide and also in India is actually going on. Microfluidics also, many and most of the cases experimental microfluidic devices are fabricated using Sylgard 184. So, it is a very popular material now, and you already know what is there. So, it has a cross linkable material. It comes in two parts. So, this is the part A and this is part B. All you need to do is you need to mix them. As you mix them, it's in a purely viscous state. Then you thermally anneal it. It transforms to an elastic state, and that elastomer is what you actually want. So, this is replica molding in a nutshell. What you need is a lithographically fabricated master with relief structures. This is something you need, and this is the master or the mold or whatever you want to say. This is analogous to the mask you need in photolithography, because this is where it contains the original pattern. How do you get this? Well, you can use either of this focused ion beam or electron beam lithography to create these masters, but you can also use photolithography itself to create this master, maybe a patterned photoresist layer or an etched barrier layer. You do not go all the way up to the doping and all that, but that itself serves the purpose of your master. What is the advantage of soft lithography? That is something we will see right now. So, what you do? What is this? This is in fact at room temperature a freshly prepared mixture of A plus B of your Sylgard 184. Many people refer to this as PDMS, which is correct, but Sylgard 184 is not pure PDMS, it is cross-linked PDMS. So, please take care, because PDMS is not an elastomer. At room temperature, PDMS is a liquid. Sylgard 184 is cross-linked PDMS, that is fine, or you can use the commercial name also, that is also perfectly understandable. But this is not the only thermocurable elastomer. There are other competing products also available in the market. So, all you do, you take a beaker, you mix requisite proportions of A and B in that. As you try to mix, it is a very high viscosity. So, this part A is a very high viscosity liquid. So, as you try to mix, there will be lot of air bubbles entrapped in the mixture. So, one can do some bit of degassing by putting it in a vacuum desiccator, or one can just wait for some time for the bubbles to sort of float up and disappear. Typically, one does a bit of vacuum exposure, so that the solution is bubble free. Simply pour it on the, this is the original A plus B mixture, pre-polymer mix as it is called. You pour it on the relief structure or the lithographically fabricated master you have. So, this is what you have, because of slow dynamics, this is in a liquid form. So, it will slowly fill up conformally the contours of the stamp, it gets completely filled up. You take this this whole so you keep the master in a petri dish or something, and you take the whole thing and put it in an oven for curing at, let us say 100 to 120 degree centigrade for a requisite duration of time, maybe 4 to 6 hours. This cross links now, and as it cross links, it is like a rubber. So, once you take it out, you can simply peel it off from one side, right, and what you have is you have created not a positive replica, but a negative replica of the original stamp in this Sylgard material or this flexible polymeric material. And it is this block of that flexible material which is used as stamp for most of the soft lithography techniques, which says that it requires a flexible stamp. So, other than replica molding, almost all other soft lithography techniques uses a stamp that has been made by replica molding. Interestingly, in most cases a replica molding uses a rigid stamp. You can do clever twisting of processing conditions by which you can in fact use a Sylgard stamp to replica mold Sylgard, but it requires certain additional modifications, and that is not the most common thing people would do. So, that is it. I mean, you have already learnt one soft lithography technique. It is just sort of molding what you have done in your childhood, only the structures are very, very small here. What you need to understand is that once you have a stamp, let us say which has very narrow dimensions, right, there is in principle no difference, no restriction why those small dimensions cannot be replicated on your replica. So, there is it is no longer limited by diffraction of light, wavelength, etc., nothing like that. There are certain issues because this material is soft. So, if one tries to make very tall structures, these tall structures, and particularly if they are very narrow, if the periodicity or the line width is very, very small, they might sort of pair up, they might join up. And why do they join up? Well, you have two tall structures which are flexible, which are very close to each other. Remember that 100 nanometer deadline we talked about, 100 nanometer mark. So, if this separation distance is less than 100 nanometer, there can be some sort of an active van der Waals interaction between these two, and this might lead to pairing. So, these are issues, but these are very critical issues, and let us not worry too much about them. Replica molding works fine with in most cases. So, let us stick to that. So, here are certain properties of crosslink PDMS, and please do not worry about what is there and what is there. So, there is a very good material and it has very good thermal stability, it is biocompatible, etc., etc. It is transparent. So, that is why it is very, very popular amongst people. Next, what we do is we straight away move on to nano imprint lithography. We talk about NIL first. It's as I said, it's one of the most popular techniques, and then we will discuss the other methods. What are the basic requirements? What we require here is a film which is going to be patterned, which is the polymer film we have written, and in most cases it is a glassy polymer film. So, what does it mean? That film at room temperature is rigid. You need a mold, as they call. Mold is more of a pedagogic term used for NIL. In principle, there is no difference between this one and a mold if it is made on a rigid material. NIL in its classical form cannot work with a soft or a flexible stamp. So, you have a mold. Typically, this is made by some lithographic technique, which is fine. All you need to do is you are going to emboss this mold against the film, but if you try to do that at room temperature, as I already mentioned, the film is rigid. So, it is not going to work out, right. But now you have one unique advantage the polymers have, and that is to take advantage of the fact that if you heat up the polymer beyond its glass transition temperature, it becomes soft, it behaves like a liquid, and any soft material you can deform, right. So, that is exactly what is done. This it is a cartoon, so it should ideally capture the basic essence of NIL. So, these are the hardware elements. What we have is you have a rigid master, you have a film, and see what we do. So, first step is you simply heat up the film beyond its glass transition temperature, so that it is now soft. Then you simply bring in the stamp, press it, that is where the term imprinting comes in, nano imprint lithography. Apply adequate pressure, that is something that is not written over here, and then what you do is you simply cool down the film while the stamp or the mold is in contact. So, what would happen? What would happen is the structures will sort of freeze, because as you cool down, the viscosity again goes up, and then once it is cooled down, you simply remove the original mold and you get a negative replica of the patterns that are there on your mold on the surface of the film. It is a very, very simple technique and it is a very robust technique. The structures are pretty stable because of the simple fact that they are deformed. So, this deformed surface, in fact, one thing should click in your mind is, since the surface is deformed, as compared to a flat surface, there is now more surface area. And this leads to more energy ascribed to the surface. And yes, you actually needed to apply the external pressure to create this additional surface area. So, this whole process is not something that is in the direction of a natural thermodynamic process. You are applying extra energy to create this negative replica. And had this film been in a liquid form, there would have been some flow from zones of what? Again, you know, from zones of higher Laplace pressure to zones of lower Laplace pressure, right. And eventually, had it been a liquid, please follow this carefully, had it been in liquid state, what would have happened is eventually these patterns would have flattened out. In fact, if you heat up a nano imprinted film, once the patterning is achieved, it in fact flattens out. So, if you heat up if you are interested in creating a pattern surface for some application, you will not be doing it, but if you are interested in the fundamental science, you sometimes do crazy things which might even lead to destruction of the structures. So, if you heat up nano imprinted film, it flattens out, and this phenomena is entirely driven by surface tension, because for a film a flat surface profile corresponds to the minimum energy configuration. So, this is also important. We always know that minimum energy configuration corresponds to a hemispherical shape, but that is for a drop. But if you have a film, if you have enough material that it actually forms a film, then in fact a flat surface corresponds to the minimum energy configuration. It is simply this consideration that between 2 points the minimum distance is if you join them straight away. So, it is exactly like that. So, what you have done is, it was flat initially like here, you have patterned it and therefore, you have enhanced the surface area. So, all these areas in fact you have enhanced. So, that is why you need the pressure which creates this surface, but if you sort of reheated this film, it now realizes that it is not in its lowest surface energy configuration, therefore, it simply tries to flatten out due to what is known as slumping. But the advantage is, you are cooling down the film while it is in a liquid state, it is adhering conformally to the stamp, and therefore, it creates a negative replica. If you are using a polymer which has reasonably high Tg, let us say 100 degree centigrade, and you are down to room temperature, of course, we will understand soon, maybe in the next class, that these structures contain a lot of residual stresses, but the structures are permanent and they serve your purpose. So, this is what is nano imprint lithography. We discussed a bit of critical issues, I must admit. So, let me just quickly repeat this particular video again. So, you take a polymer film, a glassy polymer film, heat it up beyond its glass transition temperature. So, it becomes in the soft stage, bring in the stamp, a rigid stamp, press it hard, cool down while the stamp is in contact with the film, the patterns freeze, withdraw the stamp. It is easier said than done. There are several issues that we will soon realize, which are very practical issues. So, this is nano imprint lithography. It is also called hot embossing at times. So, it takes advantage of this. This is the nano imprint lithography in the most common form, the classical form, the thermal NIL as it is called, because you use temperature to heat up the film beyond its Tg. There are other variants of NIL. So, what we discussed, the most classical one is the thermal NIL. You can also have an UV NIL, and each one has its own advantages. I will not spend too much time on this, because thermal NIL is the most popular one. Solvent vapor or SV NIL. UV NIL, what you do is very simple. You take a liquid prepolymer, which is UV curable, and take a rigid stamp again, but this has to be transparent to UV. Next step is you emboss it against this prepolymer, but since the prepolymer is at liquid at room temperature, no thermal cycling is required. And how do you make the patterns permanent? This is UV curable. So, once you have embossed, then shine UV from the top. Your mold is UV transparent, so these patterns freeze now. There is in fact physical crosslink of the bonds. Due to UV exposure, and it becomes like a solid after UV exposure. So, this is UV NIL. There are advantages. One of the advantages is there is no requirement of a thermal cycling. There are issues that we will discuss in the next class, because I am running out of time in this particular class. Of course, the moment you talk about thermal cycling, there are issues like mismatch in the coefficient of thermal expansion. So, that problem is not there. You do not need the heating setup, but then it becomes limited again to very specific class of polymers or materials that are UV curable, rather similar to the photoresist, not exactly photoresist, but something that responds to UV. In contrast, glassy polymers are much more general, much more generic. So, you can handle a host of glassy polymers by the thermal NIL. In fact, solvent vapor NIL is sort of a good compromise between both of them, and I think I will discuss it in the next class. So, I will stop now, and next class also I will continue with some of the aspects, critical aspects of nano imprint lithography. Thank you.